All right, good morning. Looks like audio is good. All right, perfect. So today we have a lesson on 7.3, proving a quadrilateral is a parallelogram. Okay. All of last lesson, or rather part of last lesson, we learned what different polygons were and more specifically what a parallelogram is. Okay. And so we're going to employ a lot of what we learned yesterday into our lesson for today. Now, the start of it is that we have to look at some new theorems. Okay. And these new theorems actually don't feel quite as new as you may think. They're actually pretty similar to things we've already seen before. And so we look at 7.7. It says the opposite sides converse. Well, if we look at the diagram, that looks very similar to a diagram that we've seen before, which if were not familiar, we've seen this diagram in let me make sure I have it in my notes correctly. We've seen this in 7.3. Okay. The diagram is seen in 7.3, but the actual theorem itself is a little bit different. But we still have two pair opposites, congruent sides. Okay, and we'll keep that on the back burner for right now. 7.8 parallelogram opposite angles converse. Well, that looks a lot like 7.4. And you'd be correct, it is quite a lot like 7.4. And so we see here we have two pair of opposites congruent angles now. But this third one, this one we've not seen before, actually. We've not seen this theorem before. And so we look at it and we try to figure out, well, what does it have? Okay, well, for one thing, it has only one pair. Right? In comparison to the previous two, it only has one pair. They're still opposite, so we'll write that. One pair opposite. But notice how they're both congruent and parallel. So we have to have both. One pair opposite, congruent, and parallel sides. So we have to add both of those in there. And the theorem itself says opposite sides parallel right there. So we were pretty good there. 7.10 is going to be the same diagram as 7.6. And this is just going to say simply diagonals bisect. Okay, you can never forget that our diagonals are going to bisect each other. Remember, bisect means to cut into two pieces, two congruent pieces. And both diagonals are cutting each other. Okay. Doesn't necessarily mean that they're the exact same length, but it does mean that they're going to have two congruent pieces on the inside. And so we learn all this stuff, just to say that these theorems parallelograms. Oops, I spelled parallelogram wrong. Parallelograms. So this is kind of an important topic where we're showing now, beforehand, we were talking about triangles and how a triangle is going to be congruent with each other. This one, not anymore. We know more stuff, but about four-sided figures instead of three-sided figures. We know how to prove parallelograms. These are the four theorems that we're going to reference a whole lot. And there's another one that we'll get to in a little bit that we'll see. But for example, one, which a lot of us did as our do first, without even really knowing that this was what we're talking about. For example, one here, we want to say what values x and y make quadrilateral PQRS a parallelogram. Okay, well, remember, the properties of the parallelogram have three of them. Opposite sides are parallel, opposite sides are congruent, and opposite angles are congruent. Well, we're talking about angles. Sorry, not angles. Again, just making a mistake left and right here. Any angles here, we don't know anything. We don't know if they're going to be parallel, but we do know that we have a lot of values for our side lengths here. And so if we were to really break down like step by step, we would say, because we're trying to prove that this is a parallelogram, let's kind of assume the properties of it. So we'll say that PQ should be congruent with RS or SR. The reason being is because they're opposite sides from each other. Well, if we could say PQ is congruent to SR, then we can say that PQ is going to be equal to SR. That makes sense. And because we know that these side lengths are represented by those expressions over there, we can say that PQ is going to be x plus 9 equals 2x minus 1. We'll keep that there for right now. Let's move to the other sides. We have SP is going to be congruent with QR. And we're going to do the same steps. So we know SP must be equal to QR. And we're going to replace SP is Y, QR is x plus 7. Now, of course, if we had started with SP and QR, we can't solve for this equation, at least not with the knowledge we have right now. So we're just gonna leave it there for right now. But we can solve PQ and RS because they only have one variable, and we can solve for one variable. That's really easy for us. So of course, we're going to subtract x on both sides. We'll add 1 on both sides. We get 10 equals 2x. Divide by 2. And we're going to get, or sorry, not x, not 2x. I apologize. That 2x minus x is going to make it to where we have only 1x. And therefore, we have 10 equals x. In other words, x equals 10. Apologize. But then from here, we're going to take that x value and plug it into our other equation. So that now we're just looking for y and not looking for x2. So y equals 10 plus 7, and y must be 17. And that's pretty easy. Okay. Pretty simple. Example 2, it says for what value of x is quadrilateral CDEF a parallelogram? What we'll notice here is that we have two diagonals. Okay. And so whenever we have diagonals, immediately what we should think is bisection. Okay. When we have bisection, we see that CN and NE are congruent to each other. Again, the reason being is that they're bisection, which means that FN must be congruent to ND. And we're going to do the same thing that we did in the previous problem. Fn must equal ND. And therefore, because I know those expressions, 5x minus 8 equals 3x, and we'll solve. So plus 8 on both sides, minus 3 on both sides, 3x. We get 2x equals 8, divide by 2, divide by 2, x equals 4. And that makes sense because plug 4 into both of those equations or both of those expressions, we'll get the same answer of 12. 4 times 5 is 20, minus 8 is going to be 12, and then 3 times 4 is, of course, 12. And so from there, we're good. Here we have the summary of key point 1. This is what I was talking about earlier, where we have the 4 new theorems, which are these 4 right here. Okay, those are the 4 new theorems that we have. But we can never forget that we actually have a definition of what it means to be a parallelogram. And I've made a lot of emphasis on the last video as well. So there are actually 5 ways. 5 ways to prove parallelogram. Okay, that is what we want to leave ourselves with. 5 ways to prove parallelogram. And we're going to use those 5 ways to determine example 3. Write a mini proof to prove that each of the following quadrilaterals is a parallelogram. Okay, well, just for time's sake, we're not going to go fully in depth in each of these. We might just do one of them. But the mini proof is going to imply about 2 to 3 steps. Okay, so let's look at the first one. The first one, if we were to do it into a proof format, we'll say our statements and reasonings. What I find might be easiest is if you label your own quadrilateral, so A, B, C, and D, like so. Might be things a little bit easier, especially whenever you're writing your given. And in our given, we would basically write exactly what it's telling us in the diagram. We know that AB equals DC, which equals 30. And we know that AB is parallel with DC. And that is our given. What we're trying to do is we're trying to prove that this is a parallelogram. But what we should see here is that we've already pretty much done so. If we look back at our theorems here, kind of on your own, think about which theorem do you think we're actually going to use here whenever we have a pair of parallel sides and then the same pair of parallel sides are also congruent. We should be using the opposite sides parallel and congruent theorem. So what we'll write here is we know ABCD is a parallelogram. Parallelogram, good. Then our reasoning is going to be opposite sides parallel and congruent. Okay, that's going to be enough for us. And that's our mini proof. We're done. QED if you want to. And that's it. The main important thing whenever you're trying to do a proof for a parallelogram is to determine which way you're going to do it. Again, because you have 5 ways to prove that a parallelogram is a parallelogram. And so if we look at the second one, I want you to look at the second one and the third one and determine your own answers before we go over them. So pause the video, stop the video, and try to figure out on your own first. But of course, I'm by myself, and I can just keep going as much as I need to. And so this is the one. We have 2 pairs of congruent sides. Well, if we have 2 pairs of congruent sides, let's look back at our 5 theorems here. And would you look at that? That second one right there, parallelogram, opposite sides, converse. That's exactly what we're going to use here. So we have opposite sides, congruence, converse. Okay. Nope, just opposite sides, converse. Okay, well, that's okay. Opposite sides, congruence, converse. It is pretty much the same thing, just with the added word. Well, that's opposite sides, congruence, converse. Let's look at this third one. And we have opposing angles congruent to each other. Well, if we have opposing angles congruent to each other, I see that third one. That's going to be our opposite angles converse. This one I'm going to catch myself on. Opposite angles converse. And that one is pretty easy. Again, a lot of it is just going to be recognition. Can you see what is given to you and be able to determine which course of action is the correct one? So there's that. Then we don't actually have a key point 2. We don't actually have one. But it is a good thing to know that we're using coordinate geometry. So it's there. But something I want us to really put some emphasis on is that we're trying to show that this is a quadrilateral. Again, there are 5 ways to do that. So let's kind of list them out, right? We know by definition it would be parallelogram. We could say it's a parallelogram. Then we know the opposite sides converse, opposite angles converse, the single side congruent, and parallel pair of sides. And then we have the diagonals bisect. Okay. Well, what we're going to do is we're actually going to number them, or at least rank them from easiest to hardest. And that's what we're going to do here. We're going to say easy. We're going to say hard. So as we go down, we're increasing in difficulty. And this is what I'm going to say. Okay, I'm going to write it down. And after I write down the entire thing, I will explain why each of them belong here. So we have definition of parallelogram. That's going to be the easiest one. Okay, I don't have a lot of space, but you would write it there. Then we're going to have the opposite side, parallel and congruent. Third one will be opposite sides, converse. Almost did it again. Then we're going to have the diagonals converse. And the last one actually is going to be the opposite angles converse. Okay. Now that we have this list, I want you to think about why exactly does that just make sense to us? Why does that seem like this is the correct answer, or why this is the correct order? And so we think about it. Of course, you should just pause it and you should reflect and think about it. But we look at it and we're like, oh, we have a coordinate plane. We can't really figure out angles on a coordinate plane unless we have a protractor and it's a perfectly sized shape that we're supposed to look at. So just, we're not really going to use it, I don't think. Diagonals, we had to cross between the two lines and whatnot and figure out if the midpoint is the exact same, and that just sounds like a lot more work than we need to. It sounds a lot more confusing than we needed to be. So we're just not going to do that one. Opposite sides converse, although it's not necessarily hard to do, it's just a lot of work, right? You got to prove that the opposite sides are going to be equal to each other in length. So that means 4 distance formulas or 4 Pythagorean theorems. And in all honesty, I don't think anybody wants to do that. But then with opposite side, parallel and congruent, makes things a little bit easier. Only one pair of sides you're supposed to look for, but you're supposed to show the same 2 criteria. So parallel and congruency. And then the last one, the easiest of them all, is going to be the definition of a parallelogram. The reason why it's the easiest is because, remember, on a coordinate grid, a parallelogram or anything that's parallel will have the exact same slope. The exact same slope. So if I know this is supposed to be a parallelogram, let's say we're looking at AB. Okay, AB is going to be parallel with something. And in this case, we know it's going to be CD. This is the opposite side. Same thing here. AD is going to be parallel with BC because they're on opposite sides of each other. So in order to prove this, we have to say slope of AB and then slope of CD, slope AD, slope BC. And we're going to find our slopes. So, of course, you can use the formula, but I know a lot of us don't like using the formula. We just like to say rise over run. So I'll show it as rise over run. I start off at A. This is the leftmost point between A and B. Go up 1 unit, another unit. So I know my rise is 2, not -2, because we're not going downward, we're going upward, so positive. Then 1, 2, 3, 4, and 5 my run. And so when we take the slope of CD, it should be the exact same thing. If it's not the exact same thing, then it's not a parallelogram. Well, 1, 2. So we're good for the rise. 1, 2, 3, 4, and 5. So because we have the exact same slope, we are good there. But we still have some other problems. Let's use this dark blue. We have AD and BC. Okay, we'll start off with AD. A is the leftmost point. Start at A. Go down this time. 1, 2, 3. And because we're going down 3 units, we're gonna have a negative. Then 1, 2, 3, which of course can simplify down to just -1. Oh, I'm sorry. I was looking at BC rather than AD, which again, we should just kind of know that that's going to end up happening anyway. It's okay. Not the end of the world for us. But we will still show BC. Start at BC is the leftmost point between B and C. 1, 2, 3 to C. 1, 2, and 3. So we'll have that -3 over 3. And that's going to give us our -1. And that is pretty easy. Okay. Rather than having to deal with the square root and fractions and decimals and stuff. Just who cares? I don't want to do all that. I'm going to want to do something that's easy, which is definitely finding those slopes. Slopes definitely the easy one out of doing those other problems. And so we're going to take the same approach here for extra example 4. Of course, you don't have it in your notes, but what I recommend is that if you want some extra practice, go ahead and do so now. You get a piece of paper out or get the scratch paper from the very back of your notes and just write this problem down. But again, we're going to take the same approach. So AD is going to be not equal. I'm going to write AD is congruent to BC. And I know that AB is going to be, oh, why do I keep saying congruent? I don't mean congruent, I mean parallel. Parallel. AB, it will be parallel with BC. And that is pretty easy. From there, just find our slopes. The slope of AD, I'm going to kind of shorthand it a little bit. 1, 2, 3, 4, 5, 6, up 6 units. And then 1, 2, over 2 units, which will reduce down to 3, which means BC should also be 3. So I'm going to start at C. Okay, we gotta be careful. Start at C. It's the leftmost point. Start here. 1, 2, 3, 4, 5, 6, and then 1, 2. So we do get that 6 over 2, just like how we need it to be. And so we're good there. Looking for AB and DC. We'll start off with AB. Down 1 unit. 1, 2, 3, 4, 5. So down means negative. And we went 5 over. The same thing for DC. Start at D because it's the leftmost point. Go down 1 unit. 1, 2, 3, 4, and 5. So we can prove that this is a parallelogram. Very good. Very, very, very good. Okay. So here we're going to move on to example 5. And although I would like to do extra example 5, we'll find that these two are actually very similar to each other. Okay, so instead of doing both examples, I'm just going to do one of them. And even then, we only have example 5 in our notes. But actually, you know what? Here, you can stop the video right now if you would like some extra practice so that you can record all the information you need to in order to practice this problem. But we're still going to look at example 5. If you have any questions about how to do extra example 5, you can always just ask me some questions. Okay? So here, what we're going to do, we're going to set up our proof. So, statements and our reasonings. Always our first statement is going to be the given. So DA is congruent to BC and angle ADB is congruent with angle DBC, and that's going to be our given. And so what we'll find here is, well, I know my given, it's always 1 point on our assessments. What's also always a point usually is going to be our proven statement. So we know ABCD eventually is going to be a parallelogram. ABCD is a parallelogram. We may not know what step that's going to be, but we know it's going to be a step at some point. We don't know what the reasoning is quite yet, but we can try to figure it out. But, whew, man, at first glance, it's really hard to really say for sure what kind of theorem we're going to work with. It's giving us an angle and a side length, or at least congruent angles and congruent sides. So how the heck am I supposed to figure that out? Well, there's a trick to it. There's a good trick to it. Remember that parallelograms are supposed to be parallel. Well, given the information we have right now, we could potentially prove that something is parallel. Okay? And so the way that we're going to do this is we're going to take this figure. We're going to draw AD. Ooh, that was terrible. We're going to draw AD and BC as far out as we think we need to. Okay, again, I'm sorry, penmanship is quite bad. So we have those two. And theoretically, because this is supposed to be a parallelogram, those should be parallel. Well, if I take this transversal DB and I were to also extend it, remember, it's saying that I have some angles that are being congruent to each other. And so if I kind of shade in this region right here, this region right here is called our interior. And they're on opposite sides of the transversal, those two congruent angles. Well, if they are on opposite sides of the transversal, they're alternate. If they're on the inside, they're interior. And so the theorem that we're going to use to help us here is what we call the alternate interior angles congruence converse. This is a Unit 3 topic. We're going to use this because beforehand in Unit 3, we said that if I have a triangle, or sorry, if I have a pair of parallel sides or parallel lines, then I'm going to have the existence of what we call alternate interior angles. And that's true. Well, it's true the opposite way around as well. If I have alternate interior angles that are congruent, then I can confirm for sure that I have a pair of parallel sides, which means that our statement here is going to be AD is parallel to BC. Well, the good thing is that we're actually really close to being done with this proof. Because ABCD is a parallelogram, that's our step 3. Because, think about it, I know that I have a pair of congruent sides here, which is AD and BC. But what I've also just now done is then said that AD and BC are parallel, which means that they're going to have a little triangle. Well, if the same side is both parallel and congruent, we have our opposite sides parallel and congruent theorem. We don't have there's not a converse, it's just theorem. But this is not the only way to solve this, and I'll show you the other way as well. It's going to take a little bit more time. It has 5 steps to it, so it's going to take a little bit more time. But if you don't understand this proof method, okay, potentially you can use this other one I'm about to show you. But if you can't understand either one of them, oh boy, okay, you've gotta try to understand one of them. It's only gonna help you. Okay, you have to really, really, really try to understand it. Okay, come to the tutorials, ask me questions. Okay, but just to save on some time, I'm going to just recreate these. Right, I already know my given, so just kind of stick that there. But something that we might not have seen beforehand, I'm gonna try to erase as much as I can of this stuff. Okay. It's in a video, so it should be fine. You can just go back and pause and relook at that. But in my problem here, I have a diagram of a parallelogram. What we also know is that we have two triangles in here. And so not only do we have two triangles, but we have a side that's congruent and then an angle that's congruent. And DB is in both triangles. If it's in both triangles, that's a reflexive property. So we know DB is going to be congruent to DB. And that's our reflexive POC, property of congruence. Well, I've just now shown that I have a side, an angle, and another side in that order. So because I can say that, I can say triangle. Oh, we got to be very careful here. ADB is congruent with triangle CBD. I say careful because you want to make sure the letters are matching up. So we were able to say that because of the SAS congruence theorem that we learned in Unit 5. And because we know that these two triangles are now congruent, we can also say that the other things that we're missing are congruent. So in this case, we already know AD and BC are congruent, but that also means that AB and DC are also congruent. So because we're going to say this, we know that AB is going to be congruent with DC. And that's the topic that we call CPCBC. Remember, CPCBC means corresponding parts of congruent polygons are congruent. Okay, just to make sure you understand that, CPCBC, I'm going to write up here. Corresponding parts of congruent polygons are congruent. Okay. Now that we have that understanding, definitely would write that in your notes probably. So now I've just shown that I was given that AD and BC are congruent, but I've now just shown that the other pair of opposite sides are congruent. Therefore, I can finally say that 5 ABCD is a parallelogram. Okay, you could shorthand parallelogram with an actual shape of a parallelogram. That's fine. I don't recommend it as much just because people can get confused, right? What if you drew a square instead and you're trying to say that this is a parallelogram? Well, I don't know. Are you talking about a square or do you mean a parallelogram? You know what I mean? They're not necessarily different shapes, but a square is a parallelogram, but a parallelogram is not a square. Okay, so just make sure you're very clear about it. Okay. Then our final reason, that is going to be our opposite sides converse. Okay. And so if you have seen this entire video, then that means you are ready for that exit ticket that we did have today. Okay, so make sure you do that exit ticket in a tutorial time at an appropriate time and whatnot. But that is the entirety of 7.3. Our next lesson is going to be, that's not our next lesson review. Okay, our next lesson is going to be on 7.4, which we're going to look at special parallelograms and whatnot. But for now, I will see you next week. Okay, have a great weekend. Make sure you stay safe and make sure you're studying for that quiz. Okay, make sure you study for that quiz. Alrighty, y'all have a good one. Bye-bye.